Hello and welcome to the Chapter 11 Summary Worksheet from Stevens' Introduction to Statistics, the Think and Do book. In this worksheet, we take one problem from each of the three sections from Chapter 11 and do the problem from beginning to end. And it's worth pointing out that all of the solutions depicted here are available in the student version of the book in the back. So, whether you're an instructor or a student, you should have solutions to these in your book. Okay, so we're going to work our way 11.1 through 11.3. So this first one is a goodness of fit, it's jury selection problem, goodness of fit problem, so that's from 11.1. So here's the setup. A law student is trying to determine whether or not there's age discrimination in the jury selection of his county. And according to the data he collected, the age distribution for this county is given in this table, right? And then the age distribution for jurors, for a sample of 100 jurors, is given in the second table. And so what you should notice, so these are the distributions in the county by percentage, right? And these are the distributions by the number out of 100. So the nice convenient thing about that out of 100 is we can immediately start to look and we say, all right, 11 out of the 100 jurors came in the category of the age group 21 to 30, but in the county, 19% of the county residents age 21 or over were in the 21 to 30. So the 21 to 30 group is underrepresented in the jurors. When you look at the 31 to 40, 16 versus 18, that's pretty close. 41 to 50, 18 versus 19. 51 to 60, 20 versus 19. So those look pretty good. But then once you get to 65 or older, 35 out of 100 of the sample jurors came from the 61 or older category. So 35% of the jurors in the sample. But according to the data, that only makes up 25% of the county population. So there certainly seems to be some issues here at the lowest age bracket and the highest age bracket. Right. So we're going to test the claim that there is age discrimination in this jury selection process. Essentially, we're testing the claim that the age distribution of the jurors does not fit the distribution from the county. Right. So again, this is a goodness of fit test from chapter 11.1. So we start off with some preliminary information. And by the way, we are looking for the test statistic. And the test statistic here, I don't have it written down, is the sum of the observed frequencies minus the expected frequencies for each category, all squared over the expected frequency from each category. So you can add all those up. So we're going to create a table of observed frequencies and expected frequencies and then calculate this test statistic. But here's some preliminary information. And the total number of observations, the total number of trials here is 100. Right? That's our sample size. The number of different categories is 5, the 5 different age brackets. Degrees of freedom is just n-1 for this type of test. And we're going to conduct this test at the 0.05 significance level. All right, so the claim is that the distribution of age of all jurors does not fit the distribution of the county. And so we start off with the null hypothesis, which says that basically it does fit. There is a fit. If P1 is the proportion of all jurors in age bracket 1, then we're claiming that equals the county. We're not claiming it. The null hypothesis says that it's equal to the county distribution. Right, so that 19 comes from this 19% here. This P2 equals 18 comes from that 18, 19 from that 19, 19, 19, and then 25 from that 25. So the claim, the null hypothesis, is that the distribution of jurors actually does match the distribution of the county. And the alternate hypothesis is that the probabilities are not all equal to their respective values. So these are considered to be probabilities. All right. So the null hypothesis is that the probabilities are not all equal to the respective values shown here. Or the proportions, if you want to think of them as proportions. Okay, so we're going to calculate the test statistic, which again is right here. And in this chapter we were able to do this with a single table, which was nice. So we look at our different categories, different age categories. And the observed frequencies come from this second table, 11, 16, 18, 20, and 35. The assumed probabilities based on the frequency, the proportions from the county are 19, 18, 19, 19, and 25%. So in terms of probabilities, or decimals, we get these. So the actual expected frequencies are calculated by n, the total number of jurors in our sample, times p sub I. So this 19 came from 100 times 0.19. And likewise, 100 times 0.18. And we get all of our expected frequencies. Right. And so that's actually the nice thing about having 100 as your sample size. You can get proportions just by looking at the numbers and moving the decimal place. Okay, so now, according to our test statistic, we need to add up all of these things. So O sub I minus E sub I. So to get this first row, last column, I take O sub I, which is 11, subtract E sub I, my expected frequency, square it, and divide by E sub I. So I get 3.368. Doing that in each row, I get these individual terms, and then I add them to get my test statistic. So my test statistic is a chi-squared value, 7.696. So do we reject or fail to reject the null hypothesis? Well, if you look at, and this isn't on page 3, we're looking at table 5, the chi-squared distribution. 4 degrees of freedom, 0.05 significance level. So what do we get? Nope, got away from me there. 4 degrees of freedom, 0.05 significance level. The critical value is 9.488. So going back, the critical value is 9.488. That's where this comes from. It comes from table 5. And the test statistic, 7.696, is not in the rejection region. Specifically, if we draw this thing, and I'm running out of space here, the critical value is 9.488, and the rejection region is everything to the right. So this 7.696 is not in the rejection region, right? So we fail to reject the null hypothesis. If you're using software, you get a p-value of 0.103, and that's greater than alpha because our significance level here is 0.05. So either way, we fail to reject the null hypothesis, and we had some phrasing that we learned in 11.1, but look at it, we're failing to reject the null hypothesis. All right, so we can't really say that the distribution of jurors is different from the distribution in the county. So the way we say that, there is not enough evidence to conclude that the distribution of outcomes does not fit the expected distribution from the null hypothesis. Specifically, there's not enough data to support the claim that there is age discrimination. Right? There's not a perfect fit, but the fit is not bad enough to conclude that there's age discrimination going on. Right? So that's a goodness of fit problem. Let's take it to a number 2. This is actually from chapter 11.2, which is a test of independence. And we'll get to that in 1 second. One thing I need to do, I need to take a quick pause here. I guess not. Okay. So, we'll get rid of that. Education and job satisfaction. So, 11.2, this is a test of independence, so we're going to determine whether or not two variables are independent or dependent. So, the results of a poll from a random sample of 425 people on job satisfaction is compared to the level of education, and the results are summarized in this contingency table. Right? So we have two categories, the variables very satisfied and moderately satisfied, and we have no high school diploma, some college or associate's degree, and a college degree. So the column variable is level of job satisfaction, and the row variable is level of education. Right? And so we want to test, is there a dependent relationship between job satisfaction and education level? And we'll conduct this test at the 0.05 significance level. And the test statistic, do I have it down here? Okay, good. So I have the test statistic here. So that's nice. And I also have the way to calculate the expected frequencies that are here in the test statistic. Okay, good. So some preliminary information. N is what we call the table total, and that's over here, 425. The degrees of freedom for a test of independence is the number of rows minus 1 times the number of columns minus 1. 2 rows, 4 columns, that gives me degrees of freedom of 3. The significance level in this particular problem is 0.05. So there is no specific claim. Notice we're just looking to test for a dependent relationship. So we're not claiming that the relationship is that the variables are dependent or independent. We're just conducting a test for dependence. We want to see if there is a dependent relationship or not. So we don't have a specific claim. But that doesn't matter because our null and alternate hypothesis is pretty much already determined. All right. In fact, it's always determined for a test of independence. So the null hypothesis is always that the variables are independent. In this case, the variables are job satisfaction and education. And the alternate hypothesis is that this is not true and that the variables are in fact dependent. So we have to calculate the expected frequencies for each cell in this table. So we have the observed frequencies right here that I just circled. We need to calculate the expected frequencies. And they come from equation 11.3, which is row total times column total over table total. So this first one here, the 60.9 for row 1, column 1, that corresponds to our original contingency table of this position. And it's the row total, 242, times the column total, 107, divided by the table total. So that's the 242 times 107 over 425. So that's where this comes from. We get 60.9. Likewise, you can go to any of these. Suppose we look at this one. Second row, third column. Where did that 46.5 come from? Well, it's the second row, third column. It's this value here. That's the observed value. What's the expected value? It's the row total times the column total divided by the table total. 183 times 108 divided by 425. That's this. Gives us 46.5. So we create our table of expected frequencies. And that allows us to calculate our test statistic, where we sum up for each cell the observed frequency minus the expected frequency squared divided by the expected frequency. And so when we do this, let's take a look at this. Where did this one come from? 48 minus 60.9 squared, all divided by 60.9. So, let me see if I can get this table. So it's the 48, row 1, column 1. So it's this 48 minus the 60.9 and the corresponding cell for expected frequencies, all squared divided by the 60.9. And so that's what this one is. And then you move along. So as we look at this one, first row, last column. So that comes from the 64 here minus the 58.1 here, all squared divided by 58.1. So that gives us this one. So when we add up the observed frequency minus the expected frequency squared divided by the expected frequency, in each cell we get a test statistic, a chi-squared value of 10.548. So now we have to determine whether we reject or fail to reject the null hypothesis. So we're going to look at the critical values from table 5. That's the chi-squared table. It's not on that page. We have 3 degrees of freedom. Oops, sorry. 3 degrees of freedom, 0.05 significance level. So let's take a look what we have here. 3 degrees of freedom, right there. 0.05 significance level, 7.815. So that is our critical value. 7.815. And the test statistic is 10.548. So that is in the rejection region. And when I say that's in the rejection region, what I mean is if we were to draw the chi-squared distribution, chi-squared, the critical value is 7.815. The rejection region is everything to the right. And our test statistic, 10.58, is in the rejection region. Right? So we're going to reject the null hypothesis. If you are using software, we don't need any of this critical value stuff. You get a p-value of 0.0144, which is less than the significance level, which is 0.05. So either method, you reject the null hypothesis. So what that means, we go up here, if we just take a look at the null hypothesis is that the variables are independent. And we're rejecting that claim, or that hypothesis, that they are independent. So that's good for our alternate hypothesis. It says the evidence suggests that the variables are in fact dependent. Right? Specifically, job satisfaction is dependent upon the level of education. Right? So that's at the 0.05 significance level. It's worth pointing out that if I change my 0.05 significance level to say 0.01, I suddenly would not be able to reject the null hypothesis. And I would not be able to support the claim of a dependent relationship. Okay. So that was what? That was 11.2. Now we're going to go to 11.3. That is the chapter on ANOVA. Right? And we're going to look at student's grade versus math SAT score. So a student does a research project to see if students with different grades in intro stats courses have a different mean SAT scores in math. All right, so we're looking, do people that get a different grade in stats class do better on the SAT? Because the quantitative portion of the SAT doesn't really have a lot of stats in it. But we're looking to see if the means are actually the same or not. So the results of the sample data are given in this table. All right. So if they got an A in stats from this sample, we see a mean of 595.5. If they got a B in stats, the mean of those students, 573.1 on the math SAT. And not surprisingly, as the grade level in the stats course decreases, the score on the SAT decreases as well. But we're looking for whether or not these means are different. Right? Are those means different? And we will assume that there's a distribution of SAT scores from the different populations that are approximately normal. That's required to continue with this ANOVA test. So we also have the results of an ANOVA test here for us, which is nice because that gives us the p-value. So this doesn't take nearly as long as the other two tests. Okay, so we're going to test the claim that the mean math SAT score for all students in each group are not equal. We're going to test this claim at the 0.10 significance level. The null and alternate hypothesis, these are consistent. For an ANOVA test, the null hypothesis is that all of the means are the same. And the alternate hypothesis is that at least one of the means is not the same as the others, right? It doesn't tell us which one's higher or lower, but it does say that one of them is different. They're not all the same. Okay, the test statistic and the p-value, that's great. That took no work at all. It was given to you, and that's because, in my humble opinion, an ANOVA test should never be done by hand, but should be done with software instead. And since we don't have a software requirement for this textbook, I just give you the results, right? So the p-value, well, the test statistic is 3.165, right? But more importantly, the p-value is 0.0258, right? So when I look at what do I do about the null hypothesis, do I reject it or not? Well, the p-value, 0.0258, is smaller than the significance level, which is 0.10. Right? So I'm going to reject the null hypothesis. That's simple. P-value smaller than the significance level, reject the null hypothesis. So I reject this hypothesis that all of the means are the same. So, being more verbose about it, there is sufficient evidence to conclude that the population means are not equal. Specifically with regards to grades in the stats class and SAT scores, we say, the data supports the claim that the mean math SAT score for all students in each group are not equal. And again, the problem here is that this test doesn't tell us which ones are higher. And when you go back, you can sort of speculate that the students with the higher grade in stats did get a higher SAT score, but this test doesn't necessarily demonstrate that. It just says these means are not all the same. Right? If you wanted to compare one particular group to another, you'd have to do a two-sample test as per the test described in Chapter 9.2. Right? Okay. Quick question. Does your conclusion change at the 0.05 significance level? Well, the p-value, it's just to emphasize it here, is 0.0258. Right? And that's all we really need to answer these two questions. Does the conclusion change at the 0.05 significance level? No, because the p-value is still less than alpha. We will still reject the null hypothesis, and our concluding statement would be the same. However, if you look at the 0.01 significance level, now the p-value, 0.0258, is bigger than the significance level. And in that case, we would fail to reject the null hypothesis. So yes, our conclusion does change. And now all of a sudden, there's not sufficient evidence to conclude that the population means are not equal. So suddenly we can't say that those means are different. Right? We didn't say that they are the same. I can't emphasize this enough. This, failing to reject the null hypothesis doesn't mean we proved it to be true or support it. All we're saying is that there's now not enough data to conclude that it's not true. Right? So we didn't prove that it's true. That's as good as any sort of final take-home message here. You don't ever really prove that the means are equal. That's very hard to do. But we have said, well, there's not enough reason to believe that they're different. Okay. So that wraps up the Chapter 11 summary worksheet. And I believe ends our video lectures for this book. It has been fun. It's taken a long time. And I am happy that we've concluded this book. I hope you took the course and did well in the course, enjoyed the course, somewhere in between enjoyed it and tolerated it. But it's been a pleasure giving you these video lectures, and I hope you take a second course in statistics. Bon voyage.